Hey guys, welcome to my YouTube channel Tech Guru Gautam Prasad. The link is www.youtube.com/@ Gautam Prasad 101. So you can visit this YouTube channel to have more videos on these other various subjects. I'm also expert on the following subjects: computer basics, IT applications, IT development, electrical technology, electrical machines, etc. Electronics, basics, and advanced, crane operation, crane maintenance, and industrial rigging. This video of mine is going to be on induction motor, the three-phase induction motor. So why these AC motors are more preferable in the market? So AC generation is easier. AC power generation is easier comparatively, and it can also be AC power supply can be stepped up or stepped down, and it can be rectified to DC as well. Uh, Common and frequently used in the industry is AC power. Uh, what is the advantage of having three-phase induction motor? So let's try to explore this. Is the simple in construction AC three-phase motors are, and they have got better reliability, low cost, high efficiency, less maintenance, and they are also self-starting in nature, and also they have good power factor they operate on. So these are the uh, set of advantages why this three-phase induction motor is used in the market extensively. Here is a picture of three-phase induction motor where you can see it has got a rotor and a wound stator. So there is a winding on the stator. Uh, Now let's try to know its constructional details. As you can see in the picture, there is a stator and it has got a core, you know, a stationary stator consisting of the steel frame that supports the hollow cylindrical core. Hollow cylindrical core. Because at this place, the rotor will be fixed. The core is constructed from stacked laminations. They are laminated to reduce core losses, and having the number of evenly spaced slots in which stator windings will be placed. So that is it. Now let's try to understand the rotor part. The rotor could be a squirrel cage induction motor, a squirrel cage type of the rotor, or wound rotor. So in the case of the wound rotor, you will have winding on the rotor, like you have the three-phase winding on stator. The three-phase winding is also there on the rotor. So it also has three slip rings, to connect external resistances, and with those external resistances, you can um, speed control the speed of the three-phase induction motor. But in the case of squirrel cage induction rotor, in fact, there is no three-phase winding as such, but there are bars placed in the rotor slots, and those rotor bars are shorted at the end with the help of end rings. There is no slip ring as such in these squirrel cage induction rotors. Rather, they are shorted and form the closed circuit of the rotor, and they rotate because of the induced EMF in the rotor. So, in principle, both of these uh, rotors operate in the similar way, not exactly same, but in similar way. So that is it. Let's try to understand now. A revolving rotor composed of the stacked laminations. Again, like your core, stator core was laminated, your rotor core is also laminated. With rotor slots for the rotor winding with any one of the two types of the rotor winding. Conventional three-phase winding made of insulated wire or aluminum bars shorted together with the help of end rings. Now the two basic types of designs of the rotor, squirrel cage and the wound rotor. So as I told you, these two types. Now let's try to understand more about the wound rotor. Wound rotor is complete set of the three-phase winding, usually star connected, and the ends of the rotor wires are connected to three-phase slip rings on the rotor shaft. External resistance is connected in each winding at starting to generate more torque basically, and so it reduces the starting current also, and improves the power factor at the same time. Higher rotor resistance at the starting increases the starting torque. As the motor speeds up, the resistance in the rotor circuit gets cut step by step. The rotor is short circuited so that it runs at the highest speed and delivers the load torque. Okay, now let's try to understand the construction of the rotor. You can see in this picture that there are three slip rings here and three brushes are there placed on those slip rings. So with the help of these brushes, the external resistance is connected. Now let's try to understand how many types of induction motors are there in the market. So there are two types, as I told you, the squirrel cage induction motor and the slip ring induction motor. What is the difference construction wise? It is very simple. I mean, the squirrel cage induction motors are very simple. On the other side, slip ring type motor rotor has winding, so its construction is not simple, little complicated as compared to squirrel cage induction motor. Cost wise, if you see, the squirrel cage induction motor is uh, less costly, whereas because of the winding on the stator and the rotor, slip ring induction motors are more costlier than this squirrel cage induction motor. Uh, as far as the starting torque is concerned, a squirrel cage induction motor possesses less starting torque as compared to slip ring induction motor, which has higher starting torque compared to SCIM. Uh, Efficiency wise, if you will see, the efficiency of a squirrel cage induction motor is high, whereas that of the slip ring induction motor is low. The power factor is less in the case of a squirrel cage induction motor, whereas in the case of slip ring induction motor, power factor is higher. The starting current is very high in the case of a squirrel cage induction motor, but in the case of slip ring induction motor, it can be reduced by adding resistance in the rotor circuit, so starting current is lesser as compared to SCIM in SRIM. No slip ring is there in the case of squirrel cage induction motor, as its conductors are shorted with the rings and they are not connected to the outer circuit, outer resistances, external resistances. So there is no question of any slip ring in this case. So that is why it is less costly as compared to SRIM. Brushes on the slip ring sparks in the case of the slip ring at higher loads, especially. So this is the most important part of the uh, three-phase induction motor, the creation of rotating magnetic field with the help of three-phase supply. So when the stator winding is fed with three-phase supply, which is 120-degree apart from each other. All the three phases are 120-degree apart. Uh, with respect to each other. So this is fed to the three-phase uh, winding of the stator. A rotating magnetic field with a constant magnitude is produced, rotating with a speed of synchronous speed basically, and that is given by n sync equal to 120 f, that is supply frequency, divided by p, that is number of poles, and it is given in rpm, rotations per minute, where f is supply frequency, p is the number of poles, and n sync is the synchronous speed, as you have just explained it. The rotating magnetic field is created with the help of the three-phase supply that I'm going to show you in the subsequent slides. Here is the three-phase supply, and it seems to be rotating. As you can see in the picture here, this rotating magnetic field has been shown. It is constantly shifting, uh, and you can see the size of the arrow of RYB are diminishing and increasing in a very orderly fashion, and when two are reducing, the one is increasing, and that is how it happens. And the magnitude of the flux in the space magnetic gap, basically air gap, that is called air gap, is maintained to be constant. So the three-phase waveform follow each other in the sequence of ABC, and that produces clockwise rotating magnetic field. If we interchange any of the two phases of the line connected to the stator, the new phase sequence will be ACB, and the rotation will be reversed. So if you want to reverse the rotation of the three-phase induction motor, you just have to interchange two phases, any two phases, not as such any two specific, but any two phases you have to interchange, and the rotation of the three-phase induction motor will be reversed, and that you have to do on the stator side. Now, how does it vary? How the number of poles affects the number of your rotations per minute. So for two poles it is 3000, for four poles it will be 1500, for six poles you have to substitute the values 128 by p, and you will be getting the number of rotations per minute. So for different number of poles you will have different speeds. Induction motor sleep. So there is something called sleep exists in the induction motor, and that is given by ns minus n divided by ns. Ns is the synchronous speed, and n is the actual speed of the induction motor at which it is running. So s is equal to basically difference of ns and n divided by ns, synchronous speed, multiplied by 100, and it is often represented in percentage or decimal. So S is the slip, Ns is the synchronous speed, N is the actual speed of the motor. At no load, the slip is nearly zero, less than 0.1%. At full load, the slip for the large motors uh, uh, rarely exceeds 0.5%. And for the small motors at full load, it rarely exceeds a certain value that is not visible, but it is near about 0.5%, and sleep is 100% for the locked rotor. 100% for the locked rotor. That is one. Sleep is one. If you will see in decimal, sleep is one basically. So frequency of the induced EMF in the rotor. With the help of, as you have studied Faraday's law of induction, whenever some conductor will cut the fluxes, as because the stator flux is running and they are cutting the rotor conductors. So EMF is induced in this rotor conductors or rotor bars in the case of SCIM, and rotor conductors in the case of SRIM. So these, rotor bars or rotor conductors uh, uh, have EMF induced in them, and that is also AC in nature. So, as because the relative speed is more in at the beginning, the frequency at the beginning when it is starting, just to start, it is equal to the frequency of the power supply, that is 50 hertz in the beginning, and as it starts rotating and gathers speed, it uh, starts diminishing also, and goes up to five hertz or 3 hertz at the end of the, when it speeds to the full speed, it speeds up to the full speed when the rotor starts rotating at the full speed. So when the rotor is blocked, that is, it is stalled, slip is 1. The frequency of the induced EMF of the rotor is 50 hertz, as I told you. If the rotor runs at the synchronous speed s equal to 0, the frequency will be 0. When FR frequency, where this FR is the frequency of the uh, EMF, and frequency of the supply, basically, frequency of the supply, and current in the rotor. No, no, no. FR is the frequency of the voltage and the current in the rotor, and F is the frequency of the supply. S is the slip. Induction motor is speed. If the rotor runs at the speed the same as the speed of the rotating magnetic field, then the rotor will appear stationary and the rotating magnetic field will not cut the rotor. So this is a very unwanted situation because no EMF will be there in the rotor circuit. So it will uh, uh, that situation is not possible, because there has to be a, for the conversion from electrical to mechanical power, some EMF must be there in the rotor circuit. So no induced current in the will flow in the rotor, and no torque will be generated. So as I told you, for this conversion to mechanical energy from electrical energy, this is essential. Some EMF must be there in the rotor circuit, and subsequently some current must be there, so that this conversion keeps on taking place. So when the speed falls, the rotating magnetic field will cut the rotor windings, uh, uh, and the torque is produced. This part I have already explained you. Induction motor speed. So induction motor will always run at the speed lower than synchronous speed. It is not going to assume the synchronous speed uh, at any particular time. So the difference will always be there in the speeds between the synchronous speed of the stator, where the rotating field is, the field is rotating at the synchronous speed, and the rotor is rotating at a lesser speed as compared to synchronous speed. So n slip is nothing but the slip speed is nothing but the difference between synchronous speed and the actual speed of the motor. Now let's see, this is the equivalent circuit of the induction motor, where it has been shown that there are two parts. On the left side, you have the stator part, where you can, if you have studied the transformer, you must be remembering that the circuit is more or less like that. Okay, and on the right side of the circuit, you have a closed circuit. So basically, sometimes induction motor is said to be a transformer with closed secondary. So here, the equivalent circuit has been shown in terms of transformer, where the left side is given the supply and the right side is shorted to build EMF and rotate